Alright, yesterday we talked about three men. We talked about Millikan. Millikan used the cathode ray tube to determine that the mass of an electron was very, very small, about 2,000 times less massive than a proton. Thomson used his work with the cathode ray tube to determine that the electrons had a negative charge. From that, their work, other scientists determined that the atom had to have something positive to balance that negative electron, and there had to be something heavy since the electrons were so light and the atoms were heavy. So this gave them a direction for their research. So Thomson's model was that this area is a huge like pudding with little nuggets of negative. So it's a plum pudding. So the entire scientific community agreed that that was what the atom was going to be like. Of course, this has changed over time. For a long time, they couldn't find the positive, so they thought this plum pudding was probably going to be the right thing. And the other pieces in the atom that were found around this time was the proton, which is positively charged, the neutron, which has no charge, but a mass of about the same as a proton, but they didn't know where these pieces were. They thought they were evenly distributed in this pudding. Then along comes Rutherford. Rutherford made a major breakthrough. He still believes in that plum pudding model. So everybody in the scientific community believes this plum pudding model. And so he sets out to prove it with his new method, with his experiment. So the alpha particles are positively charged particles given off by uranium. Remember I said yesterday that you have to know that that's what it is, that alpha particles are positively charged particles. And he's going to shoot them at this gold foil. Alright? So when the alpha particles hit his fluorescent screen, it's going to glow. This gives him a detection of when these particles hit, because he can't see them. He can only see the aftermath. So this is what his machine looked like. The uranium is in here, and she's going to use the uranium to shoot to his gold foil and through the gold foil, and he's going, and this is going to be his experiment, and he's going to expect everything to be centered at this point. So the next part of this is he starts his experiment. Alright, so here's his experiment. What he expected to happen was that these alpha particles were going to go straight through, because he's shooting his gun, his 40-06, at a plum pudding, so it should go straight through. So as he shoots it, this is what he expected. Now, again, why did he expect this? Because he's shooting this powerful gun at a pudding, so he's not expecting anything to really be substantial to stop the bullets from going straight through. But that's because of this plum pudding that he expected. He's going, these evenly distributed, that bullet should go straight through. Now, this is what he got. Whenever he shot at the what he thought was going to be plum pudding, first thing you notice is that this part of the line is a lot smaller than he expected, and then as he continued to shoot at it, he saw this happen. A scattering of these alpha particles striking his fluorescent screen in various places. And as he watched, he saw that was not only on this side of the gold foil, but some of them actually bounced back toward him. So he had to revise all the things that he thought was going on. His theory was wrong, so he had to come up and develop a new theory. So this is how he explained it. There must be the atom must be mostly empty, because most of the alpha particles went straight through. So most of the alpha particles went straight through because they didn't touch anything. but there had to be something at the center that was small and dense and positively charged. Why did it have to be positively charged? Because the alpha particles were positively charged, and like charges repel. So if I shoot a positive bullet at a positive object, they're going to repel each other. So this small positive dense center helps explain what he observed. And the alpha particles only get deflected when they're close enough to that positive charge. All right? So this is what he observed. So notice that this, get my pen, this is deflected a little bit because it's kind of a long way from the positive. This one is deflected a lot because it was a lot closer, and then this one bounced straight back because it was headed straight at this heavy, dense, positively charged center. All right? So the modern view is that the atom is mostly empty space. It has the nucleus where the protons and the neutrons are located, and it has the electron cloud, which makes up most of the volume. And most of this is, we're not going to talk about the density so much, but we want to know that that positive nucleus is small and dense. Remember that if we were to enlarge the nucleus the size of a marble and put it in the middle of Mississippi State's football field, the atom would be the size of that huge stadium. So it is very large. You're going to need to remember that electrons E minus, protons positive P, and neutrons is neutral. The relative mass of these, whoops, went too far, let me back up. The relative mass of these is what's important. So we're going to say the relative mass of an electron is 0. The relative mass of the proton, that means when we compare them to each other, is 1. You do not have to know these numbers. You only need to know that an electron is a 0 and the proton and neutron are 1. The charge of an electron is -1. Charge of a proton is +1. Charge of a neutron is 0 because neutral means 0. All right, let me get my pointer again. Two regions. The two regions are the, now, there's a difference between the three parts of an atom. The three parts of an atom are proton, neutron, electron. The nucleus of the atom is a region where we have protons and neutrons, and with a positive charge, and then we have the electron cloud where the volume of the atom is, and it's negative. The electron cloud are where the negative electrons are. So where's the mass located? The nucleus. Where's the mass located? The nucleus. And the volume of the, gotta back up again. Get my pen here. The mass is in the nucleus, and the volume comes from the electron cloud. So that's an important point that we need to remember. All right, get my pointer so I can go on to the next slide. This is where we talked about the size. We're not going into all these little numbers. The only thing we have to know is that the nucleus is extremely small compared to the size of the atom. All right, now this is new. The atomic number. The atomic number is the number of protons in the nucleus. And this determines what kind of atom we have and the number of electrons. Now, I'm going to write here a short little formula that you're going to be using, so you'll need to write this down. The atomic number equals the number of protons. Whoops, made that a little bit overly done, didn't I? The number of protons, and it also equals the number of electrons. Alright, so atomic number tells us the number of protons and the number of electrons. Every atom of carbon, for example, has 6 protons. Its atomic number is 6. And the number of electrons in a neutral atom is 6. So when you look on your periodic table and you see the boxes, I'll draw a box here, and we look at carbon, it'll have a big C in the middle. It'll probably say carbon down here. Best I can write with this pad. And it's going to have a 6 and it's going to have a 12 in here. 12.01 probably in here somewhere. This is the atomic number. So every carbon atom has 6 protons and 6 electrons, and its atomic number is 6. So looking at your periodic table that I gave you the other day, you can see that the boxes are numbered 1, and then way over here is number 2, and back over here is number 3, 4, and then we have 5, 6, 7, 8, 9, and they're numbered sequentially. Those are the atomic numbers, and every one of those represents the number of protons in that atom. The next little formula you need to know is mass number. Alright, the mass number equals the number of protons plus, let me just put the symbol for P for proton so I'll have room. The number of protons plus the number of neutrons. So the mass number is going to equal the number of the protons plus the number of neutrons. Another way that you might have to use this is the mass number minus the number of neutrons is equal to, let me change that, I don't like that one as usual. The mass number minus the protons is equal to the number of neutrons. Now, if you look at this, what I've done is I have done a little bit of algebra. I've subtracted the number of protons from both sides, and I get this new formula. So the only real formula I need to learn is this one, but I do have to solve it for neutrons sometimes and for protons sometimes, which we'll see over the course of the next few slides. Alright, so I'm going to erase this, and I'm going to the next slide. Alright, isotopes. Dalton was wrong. One of his second thing on the list of Dalton said that atoms of the same element were the same mass, the same size, and the same properties. They are the same size and the same properties, but they are not the same mass. And they are not the same mass because we have what's called isotopes. Isotope atoms are the same element and the same number of protons. Let me get something to draw with, then change my color. I'm tired of that black. So let's go to the same number of protons and the same atomic number. What did I just say a minute just on the previous side? Atomic number equals the number of protons. The number of protons. And what have we said right here? The same number of protons, the same atomic number. That's like a double negative. I'm saying the same thing 2 times. The same number of protons is equal to the the number, the atomic number. So you really need to know that they're the same element, they have the same number of protons. So you're actually kind of saying that twice. Alright? Now, the isotopes also have different numbers of neutrons and a different mass number. And we call this an isotope. So if the number of protons has to be constant for any atom, for every carbon atom, every carbon has 6 protons. But not every atom has 6 neutrons. Some of them have 8 neutrons. So an atom of carbon has to have 6 protons. But it can have different numbers of neutrons. They're neutral, and they don't have anything to do with anything but the weight of the atom. The number of neutrons in the atom is what makes it heavier. The number of protons in the atom is what makes it carbon. It has to be that number of protons. Let me get rid of this little writing and go on to the next thing. The symbols. One way of noting the symbol of an element is this notation. This would be the X represents the symbol of the element, and then the mass number is written on the top and the atomic number is written on the bottom. So let's pretend for a second that we know that this particular element is, we're going to use carbon again. The symbol for carbon is a C. And if I put 14 up here and I put 6 down here. Now I'm going to ask you the question. How many protons? So I'm going to put a P up here. How many protons are there in this atom? Everybody think about it for a second. Write it down on your own sheet of paper, and let's see if we got it right. Where's the atomic number? It's down here. The atomic number, we said a minute ago, equals the number of protons. So that would make protons be 6. Now the question is, how many electrons are there? Well, a minute ago when I wrote this formula down, I said atomic number equal number of protons equals number of electrons. So the electrons is also 6. Now the final question is, how many neutrons are there? The formula I wrote a while ago was mass number equals the number of protons plus the number of neutrons. Alright, I need to know this number. So I subtract protons from both sides. And my new formula is mass number minus protons is equal to neutrons. So my mass number, 14, minus my protons, which is told by the atomic number down here, and I've already written it up there, is 6. So my number of neutrons in this case is 8. So you'll be doing some problems using this idea. One of the things, if you don't know where the mass number is and where the atomic number is, it's going to make it really hard to work some of these problems. So make sure that you pay attention to that symbol notation. Alright, so we're going to do a couple of problems here. Now, here's my symbol. Think in your mind. What is the 19? What is the 9? What do they represent? Now, don't say anything to your neighbor, just think about it. Now, here's the question. I want you to find the number of protons, the number of neutrons, the number of electrons, and the atomic number, and the mass number. My goodness, I got all this stuff for you to find. Think about it. What's this number here? It represents atomic number. And that we know from a while ago that the atomic number equals protons and it equals electrons. Notice I'm dropping that number business. So if the atomic number is 9, I can go ahead right here and say 9. If the atomic number is equal to the protons, how many protons do I have? 9. How many electrons do I have? 9. Now I need to fill in these two. Well, we said a minute ago that this was the mass number. So what's this question? Mass number. So it must be 19. And our other formula that we have to know is mass number is equal to protons plus neutrons. I need neutrons. Subtract the P from both sides, which is going to give me over here mass number minus protons is equal to N. Mass number is 19 minus 9 equals N. Get your calculator out because I know you're going to need it. And so the answer, of course, is 10. All right? Now, the next slide, the next several slides, you're going to be on your own for a few minutes. So right now, we're going to turn off the video. I'm going to stop it. I'll start it. We'll start it back up in about 10 minutes. So you got about 10 minutes to do the next few slides. Talk to your neighbor if you need to, but get all the answers down because I'm going to be working it over the after a short break. So